We are discussing the nuclear fuel rod problem exercise. We have modeled the problem as Poisson's equation. We have discretized the Poisson's equation and developed a system of linear equations. Then we have revised the Gauss-Seidel method, which we'll use for solution of the linear equations. Now, before we actually implement it in the code, we have to decide few things. First, the boundary conditions, and second, the stopping criteria. So let us see that how we are going to implement all these nitty-gritties in the code, and then in subsequent lecture we'll go to the code itself. Let us recall the problem at our hand. Here we are having the Poisson equation as the governing equation, and we have Neumann boundary condition in two sides, here and here, because of symmetry, and convective boundary condition on two sides, which are connected to the outside fluid. We wish to solve the above system using Gauss-Seidel successive over-relaxation, because after discretization, we have this AU equals B equivalent of this system. So let us first check how we'll treat the boundaries here. First, of course, we have already developed the linear equation that will come for the interior point, that is I equals 2 to nx minus 1 and j equals 2 to ny minus 1. Here I goes from 1 to nx in x direction and 1 to ny in y direction. So the boundary conditions will be applicable at x equal to 0 and x equal to 1, which corresponds to I equals 1 and I equals nx. And also in y direction, y equals 0 and y equals 1. So let us first try this two. At x equal to 0, this is insulated or symmetry boundary. Del theta del x is 0. That is gradient in this direction is 0. X equals 1. This is Robin condition, del theta del x plus bi theta equals 0. So if I take this del theta del x 0 here, I know that here I have this I equals 1, and then I'll go in this direction in subsequent grid points. To get this del theta del x here at the boundary, the simplest way to do so, and we'll stick to that, this theta I plus 1j, so this is my I plus 1j, and this is my ij point. At the boundary I have ij. The next point is I plus 1j. I do not have an I minus 1j because I minus 1j goes left side of the boundary. So it starts from ij here. Here I is actually 1. So ij here means this is 1j, and I plus 1j means this is 2j. And the forward difference here is 0. Del theta del x I am approximating as a forward difference. It is possible to use a 3-point forward difference or higher. That will give us better accuracy, but this is only for our learning exercise. So the simplest implementation is a 2-point forward difference, that is I plus 1j minus ij divided by delta x equals 0, and that gives us a linear equation, that is ij minus theta I plus 1j equals 0, and this is applicable for I equals 1. Similarly, for I equals nx, that means when I am here, this corresponds to I equals nx, and here del theta del x plus bi theta equals 0. So here ij falls at the boundary. We do not have an I plus 1j. What we have are grid points on this direction. So I have I minus 1j, I minus 2j, etc. etc. Once again, the simplest way to write del theta del x here is theta ij, that means at the boundary, minus theta I minus j, that means inside the domain. This is a backward difference, plus bi this is theta ij, that means at the boundary equals 0. Please take a look at this distinction. Here we are using theta I plus 1, but here we are using theta I minus 1. At this boundary I equals 1, we are at left side boundary, so I minus 1 doesn't exist. Similarly, at x equal to 1 or I equals nx boundary, I plus 1 doesn't exist. All we have is minus 1. Therefore, the derivative we have approximated as a backward difference, theta ij minus theta I minus 1j divided by delta x. So now we multiply with delta x, and what we have is theta I minus 1j minus 1 plus delta x multiplied by BO number. This relation is applicable only at I equals nx, means this right side boundary. In a similar way, you can develop boundary conditions at y equals 0 and y equals 1. Y equals 0, once again, this is insulated type boundary. So what will come here is theta ij minus theta ij plus 1. So at y equals 0, this is my ij, and I can only go up to go, this is I, j plus 1. I do not have a j minus 1 here. So derivative will come from ij plus 1 minus ij. So this will be 0. And similarly y equals 1, that means this goes j equals 1 and this goes j equals ny. Here we are counting from 1 to ny in j direction, 1 to nx in x direction. If you count from 0, then you have to put 0 here and 0 here. During programming in Python, we have to count from 0 because there it starts from 0 by default. If you are programming in some other language such as MATLAB or Julia or Fortran, you will start counting from 1. So that is a programming specificity, but mostly the standard notation that we use, we always start from 1 in standard notation. So here y equals 1 is here. I have in j equals ny, that is y equals 1. And here I can have j minus 1. This is my j minus 1. But I do not have j plus 1, that will go outside the domain. So now I have 4 boundary conditions, you see. This is I equals 1, I equals nx, j equals 1, j equals ny. And the internal points are given by this I 2 to nx minus 1, j 2 to ny minus 1. This is already taken care of from this equation. Then 4 boundaries we are taking care with these equations. You can see clearly they are also linear equations. So they are simply adding to our Gauss-Seidel A matrix. Now one subtle point here, as you implement these boundary conditions, you can see that these corner points are, you are counting twice. These 4 corners, you are counting. If I count I equals 1, that means I am counting this boundary. So I am going from the bottommost point from the topmost point. But then again, when I am counting j equals 1, I am going from this leftmost to rightmost point. So this point I have counted twice. In this way, all the corner points I have counted twice. So in reality, we should not do the calculation twice here. You take it only once. So for instance, if I equals 1, that means I am at this boundary. Let us say I calculate for j equals 1 to ny, all the points I take. I equals nx, once again I calculate for j equals 1 to ny. I take all the points. Then all my 4 corner points are taken. So when I'll be going for this y equals 0 and y equals 1 boundary, I should not bring these corner points once again. So the way to do it, that here when j equals 1, I'll put this for I equals 2 to nx minus 1. For j equals ny, once again I'll put I equals 2 to nx minus 1. So corner points are counted here in x condition, not in y condition. That way corner points are counted only once. Now you can count the corner points in y also. Then in x direction you have to take 2 to ny minus 1, 2 to ny minus 1. In y it will come 1 to nx, 1 to nx. Whatever you do, that is fine. Corner points are always a problem in computation of such problem. But here it will not give you any trouble because we have this Neumann-Robin type condition. It will not give you trouble. If you have Dirichlet type condition, for example, if you have theta equals theta 1 here and theta equals theta 2 in this corner, then in these two boundaries, then you have to decide what theta you will put at the corner points, and that sometimes could be a subtle decision. But here, because of this Neumann and Robin type condition, we will not face any problem about corner points, but you have to deal with them only once and not twice. If you deal with them twice, then it may give you some problem in convergence of solution. All right. So now let us look at the stopping criteria. We know what is the stopping criteria, but how we are going to exactly implement that in our solver. We know that ui is uik plus 1 plus correction. When the correction is small, we will have this stopping, we will stop iteration, and correction is ri divided by aii. Ri is bi minus everything on left hand side in an equation I. So Ri anyway we are calculating during our usual calculation, during our update of this ui. So what we do, we have to take this norm. So R is kind of a vector for Ri, are the components of that vector. So we take the norm 2. So I square this r's and take a root. Just it will give us sort of, if I do 1 by n, then it will give us this RMS value of this R, or kind of error in each of this on an average. So this is a norm mathematically, and it is also giving us the kind of correction it is we are using on an average in one of them. So you can use this as your stopping criteria. That is one way. Another way is that you take this Ri from all the equations I and take the maximum value of this Ri, where this I goes from I goes all the way through all the equations, and you pick the maximum, and based on that you can stop the iteration. That is possible, but it is easier to implement. So you can go with, for us in this code, you can go with this one. And we will finally stop iteration when this particular quantity will be less than epsilon. So we have to set some value of epsilon. Epsilon is user defined. For the present case, we'll set epsilon is 10 raised to minus 6. That is quite all right for this kind of solution. Once you run your case and solve it, you can plot the results. So for example, this is a contour plot that I have plotted for this solution, and it will change, this contours will change with BO number. BO number is the only parameter here, so it will change with BO number. And you can clearly see that these two sides are showing symmetry. That is why it is almost contour lines are cutting vertically. The temperature is small outside, and as you come near the center, this is 1/4 of our fuel core. So we have similar mirror image on left side and mirror image on bottom. Then it will give us the complete picture. So here you can see they are cutting vertically because of this symmetry condition. And as you come from periphery toward the center, here you see maximum temperature. These are giving dimensionless temperature, which is running from 0 to 0.35. And this dimensionless temperature here is pretty higher as compared to the outside. So here the temperature is almost T equals T infinity. It is coming close to 0. Of course, how it will come, that depends on BO number. If your BO number is on the higher side, then you will find that your outside temperature will come close toward this T infinity. If it is on the lower side, then you will get a more of a gradual change. You will see that it will go toward isothermalization, means that the temperature gradients inside will be smaller if your BO number is small enough. That is something those who have studied heat transfer, we call that lumped condition. But anyway, you will reach this solution if you implement it. I'll of course not implement this for you. What I'll do is that I'll show you a simpler problem, solution of a simpler problem, and then I'll encourage you to extend that simpler code for your exercise code. And we'll discuss that simpler code in next lecture. So for now, we have implemented the nuclear rod problem in Python. Of course, we have not implemented, but I have implemented, and from there this result is coming, which I am showing. For your exercise, when you solve this problem, you change the value of Bi and you identify when the solver produces error. Every solver will have its limitation, but it is good to know the limits of your solver. To do this exercise, of course, you need to have a code first, and I'll show you how to have that code in next lecture, but you start writing your code now. Thank you. That's all for this lecture. I'll see you in next class.